Hi everyone, welcome to Modern Optimization Methods. In this part, we will introduce the last part of Chapter 4, the convergence of the trust region method. This part will include the following three parts. First, we will discuss the reduction obtained by the Cauchy point. Then we will discuss the global convergence. Finally, we will discuss some extensions. Now, let's first take a look at the Cauchy point. So recall that in previous parts, we have derived the Cauchy point. So it's basically a kind of steepest descent method with a special step length. And we have the following results, that the Cauchy point actually satisfies the following conditions. If we take a look at the condition, it basically says that the decrease provided by the Cauchy point in model function is lower bounded by the right-hand side of this inequality. So the right-hand side is actually related to the norm of gradient as well as to a term of minimum functions. So why this is important by Cauchy reduction? This result actually set up a bridge between the trust region method and its global convergence. We will show this result in the next page. So with the sufficient reduction by Cauchy point, then we can prove the following theorem. So any optimization points pk, if it is a vector provided by solving the subproblem, satisfying the following condition, which is a proportional of the reduction by Cauchy point. Okay? In that case, then we can similarly get the sufficient reduction of this point. So the reduction provided by this pk will also be lower bounded by a term here. So the term here is similar like the lower bound for Cauchy reduction, however different in the ratio C1 here, okay? It means that once we have set up the bridge of Cauchy reduction, then we can get other trust region iterations which provided better reduction than Cauchy reduction, okay? So the proof is actually very simple. We just use the inequality between the current iteration pk, whose reduction in model function will be a proportional of the reduction in Cauchy point. Then the Cauchy point will also provide a reduction like this. Then we take the first part and the last part, then we get the final result as we required. So the Cauchy point is a bridge, similar to line search results. In line search results, the tentative theorem is a bridge between the line search strategy and the convergence result. Now, we have some remarks about the dogleg method and the two-dimensional subspace minimization method. As we may recall that the dogleg method and the two-dimensional subspace minimization method will always provide better result than Cauchy point. Okay? Therefore, they will also have the similar result as we mentioned in the previous page, and they enjoyed the lower bound property provided by the dogleg method and two-dimensional subspace minimization method. So for the two ways of solving subproblem, the model reduction is always satisfied. Now, let's present the first global convergence theorem for trust region method. In this part, we consider the case that eta is 0. So recall, in trust region algorithms, we have a parameter eta. So this eta is chosen from greater than or equal to 0 until 1/4. So in this case, we only consider that eta is 0. And we have the following result. So the result is in the bottom of this theorem. It basically says that the iteration xk actually have a weak global convergence result. Okay, so notice that we have the limit and infinite, the two terms here. It actually means that we can find a subsequence of the norm gradient such that the limit is 0. Okay, so it is a weak global convergence result. And now let's take a look at the settings as well as the assumptions. So the settings is in the above. So we assume that in model function, the Hessian matrix BK, it has a bounded upper bound. So the norm of BK is upper bounded by a constant beta. And meanwhile, we assume that the function f is bounded below on the level set. So this is reasonable because we are looking for the minimum of this function. So it must be lower bounded. And then we also assume that the function f is ellipsis continuously differentiable in this same neighborhood here, all right? And for this SR0, we assume that once y lies in the level set and function f, the gradient is ellipsis continuous in this small local area. So it is a kind of weaker ellipsis continuity called locally ellipsis continuity. Further, we assume that all approximate solutions of the subproblem satisfied the inequalities. So the inequalities in the previous page actually says that the subproblem of the trust region will provide sufficient reduction in model functions. Okay? So with the assumptions here, further we assume that the length of the step pk will be upper bounded by a ratio of the trust region radius. Then we have the weak convergence result. Okay, so it seems that we got a lot of assumptions and settings. However, all of them are necessary to get the weak global convergence result. We will omit the proof of this theorem, and we go on to discuss the second case of the global convergence. The second case of the global convergence is actually the case that eta lies strictly between 0 and 1/4. For this case, we actually need another way to prove the result. So we put it in a separate theorem. The settings and the assumptions are the same as before, and also the result here is the same as before. We still get weak global convergence result. Okay? In a word, for trust region methods, under certain conditions, we can have global convergence result. However, in the sense of weak global convergence, because we only got a subsequence of the norm of gradient converges to 0. Now, in terms of the local convergence result, as we may see that, locally speaking, the trust region method is very similar to the Newton's method or quasi-Newton's method, because in a local sense, trust region method also do quadratic approximation to the problem, and Newton's method and quasi-Newton's method, they also do quadratic approximation in a local area. So from this point of view, the behavior of trust region method in a local sense should be similar like the Newton type methods. Actually, theoretically speaking, we can indeed prove the asymptotically Newton's behavior. Okay? So the settings we summarized in this page, we have some assumptions on f, that f to be twice continuously differentiable in the neighborhood of the optimal solution. And the optimal solution, we require that the second-order sufficient conditions are satisfied, which means that gradient to be 0 and the Hesse matrix to be positive definite. And assume that the sequence converges to X star. This is a very standard assumption as well. And for all k sufficiently large, the trust region method, based on solving the subproblem with bk exactly the Hesse matrix, alright? We chooses the step pk such that the corresponding sufficient reduction in model function should be satisfied. In this case, we also require that the corresponding model function reduction are asymptotically similar to Newton's step. Okay? So moreover, in mathematical sense, we assume that the current step pk behaves very similar to the Newton's direction. Okay? So the difference between the two terms is a high order of Newton's direction. After that, under all these settings, then we can present the local convergence result for trust region methods. Now, with the settings above, then we can have that there is a trust region bound delta k become inactive. So what means inactive? In other words, when the trust iteration goes on, we can find some trust region radius delta k that it will not take effect to the problem. In other words, the subproblem will reduce to an unconstrained problem. In this case, xk will converge superlinearly to X star, because locally speaking, it indeed behaves similar to the Newton's method. Okay? So this is the local convergence behavior of trust region method. Of course, we need more assumptions in this theorem. However, these assumptions indeed satisfies in real situations. Now, let's talk about some extensions. The first extension is the scaling. Scaling means that in some situations, we need to do the scaling on the variables in order to make this problem well defined. In terms of trust region method, notice that in trust region method, we actually assume that the variables behaves similar for each of its components. However, if for some particular components it varies in a large area, and for some other particular components it varies a little bit. So in this case, we need the scaling technique. So how do we do the scaling? The scaling, basically, we can introduce the diagonal matrix D to the trust region area. Okay? So originally, we restrict the trust region step length P to be smaller than or equal to delta. Now, we add a diagonal matrix D before P, meaning that we ask the rescaled length of P to within this area. Okay? So by this rescaling, then the problem seems to have better situation. Now, by this diagonal matrix, then if we take a look at the model function and the subproblem again, so we got extra diagonal P over there. And when f is highly sensitive to the value of some component and it's not that sensitive to some value of some components, then we can introduce such diagonal matrix D to represent the sensitivity of the components. And the diagonal matrix can be derived from the Hessian matrix of the problem, actually. So, introducing the diagonal matrix may provide us some new problems because, for example, for cosy-point calculation, if we got scaling restrictions, then we need to derive the cosy-point again. And we can actually have similar results as the normal cosy-point. So for this part, we call it the generalized cosy-point calculation. In other words, the model function is the same, however, the constraint changes a little bit. Then, of course, we will get different formulas. So the formulas, we present the result here, but we omit the details how we derive it. Now, the last extension is that we can also do the trust region in some other ways of norm. For example, naturally, we will use the Euclidean norm, right? However, in real practice, when you need, then you can choose L1 norm or the L infinite norm to measure the length of the vector, okay? So in that sense, it is called the trust region method in L1 norm or trust region method in L infinite norm. Of course, we can also use some extended, for example, the scaled L1 norm or scaled infinite norm. All of them are available or acceptable. So for different real situations, we may define different extensions based on the application algorithms. Now, let's make a brief summary about this part. In this part, we actually introduce the global convergence of trust region method as well as its convergence rate. All of the theorems here, we didn't provide the details. I leave you a homework to derive the results, okay? Moreover, we derive some extensions including scaling and other norms for trust region methods. Now, let's make a brief summary about Chapter 4. Chapter 4 mainly discusses the trust region methods, including the main idea, the algorithms, as well as how we solve the subproblem. Finally, we also consider the convergence performance of the methods. Okay, we stop here and see you next time.